Something is pulling our entire galaxy toward it at 1.3 million miles per hour, and no one alive has ever felt it. Not a tremor, not a pull, nothing that registers in any instrument you have ever touched or any sense you were born with. Right now, every star in the Milky Way, every planet orbiting those stars, every ocean and mountain and living thing on this particular rock is hurtling towards something enormous at a speed that makes every human achievement in propulsion look like standing still. A commercial jet moves at roughly 600 miles per hour. The fastest spacecraft ever launched by human hands peaked at around 430,000 miles per hour. The motion carrying our entire galaxy toward this object is 3 times faster than that. And nobody feels it. Nobody has ever felt it. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. The object doing the pulling does not have a clean edge. It is not a star, not a black hole, not a single galaxy. It is a region of space, a gravitational basin so massive that its influence stretches across hundreds of millions of light years in every direction, bending the paths of more galaxies than anyone has fully counted. Astronomers gave it a name that has stuck for nearly 4 decades. They called it the Great Attractor. The name is accurate in a way that most scientific names are not. It attracts. There is not much else to say about it that does not immediately become difficult to believe. Here is what makes the situation strange. We cannot see it directly. The Great Attractor sits behind one of the most impenetrable obstructions in observational astronomy, hidden by the thick dust and gas of our own galaxy's disk. We can measure its gravitational fingerprint on everything around it. We can trace the motion it produces across enormous volumes of space. We can calculate roughly how massive it must be. But pointing a telescope at it and getting a clean image the way you would point a camera at a mountain, that has never been fully possible. We are being pulled towards something we cannot look at directly, and we will never arrive. This is the other piece of the situation that takes a moment to settle. The universe is expanding. The space between us and the Great Attractor is growing even as our galaxy races toward it. Dark energy, the force driving that expansion, is winning on the largest scales. Our approach speed and the recession speed of the Great Attractor are in a race, and the expansion is accelerating. Billions of years from now, our galaxy will still be falling toward the Great Attractor. The distance will never reach zero. We are permanently in transit toward a destination that permanently recedes. This is not a minor footnote in cosmology. It is a description of where we actually live, what our actual address in the universe implies about our motion through it. The Great Attractor is the gravitational center of a supercluster containing more than 100,000 galaxies. The Milky Way is one of them. Everything in that supercluster is draining slowly toward the same point, like water pulling toward a drain that cannot be reached because the floor is tilting away at the same rate the water flows. The story of how astronomers discovered this, how they pieced together the evidence from peculiar velocities and cosmic background radiation, and eventually managed to peer through the obscuring disk of our own galaxy, is one of the more methodical detective stories in modern science. It began in earnest in 1986, with a group of 7 researchers who set out to map galaxy motions and ended up finding something that changed the scale of the known universe. The picture gets stranger the deeper you go, And the first place to start is understanding why our galaxy refuses to hold still. The universe is expanding. Every galaxy you can name is moving away from every other galaxy, not because galaxies are flying through space like shrapnel from an explosion, but because the space between them is growing. The distance itself stretches. Think of dots drawn on a balloon being inflated. None of the dots moves across the surface, but every dot gets farther from every other dot as the rubber expands. This is the standard picture, and for most of the universe, it is accurate enough. But the Milky Way is not behaving the way the balloon model predicts. On top of the expansion, our galaxy has an extra motion, a motion that has nothing to do with the universe growing, a motion that points in a specific direction, toward a specific region of sky, at a speed that becomes genuinely difficult to process once you sit with the numbers. That extra motion is called a peculiar velocity, and the Milky Way's is roughly 600 kilometers per second, not per hour, per second. Every second that passes, our entire galaxy has moved 600 kilometers closer to whatever is pulling it. Every star in the galaxy, every planet around every star, every ocean, every mountain range, every person who has ever drawn a breath on this world. All of it, moving together, silently, at 600 kilometers per second, and not one of us has ever felt it. To feel emotion, you need acceleration or friction. Something has to push against you. The Milky Way's peculiar velocity is smooth and constant enough that there is nothing to feel. No wind, no G-force, no sensation whatsoever. You are currently aboard something the size of a galaxy, crossing distances that would take light thousands of years to cover, and your body has no mechanism to register any of it. This is one of those facts that sounds straightforward when written down, and becomes quietly unsettling the longer you think about it. Consider what 600 kilometers per second actually means in human terms. The fastest crewed spacecraft ever launched, the Apollo 10 command module on its return from the moon, reached about 11 kilometers per second. That speed felt like an achievement. It was the fastest any human beings had ever traveled. The Milky Way's peculiar velocity is more than 54 times faster. A commercial aircraft covers roughly 250 meters per second. The galaxy is moving 2,400 times faster than that. In the 5 seconds it took you to read this paragraph, our galaxy has crossed roughly 3,000 kilometers. Not our solar system, the entire galaxy, all 100,000 light-years of it, dragged along for the ride. Now hold the direction in mind. This is not a random drift. Peculiar velocities can, in principle, point anywhere. Random thermal motion in a gas produces velocities that point in every direction equally, cancelling out. The Milky Way's motion does not cancel out with the motion of its neighbours. The galaxies surrounding ours are moving in roughly the same direction. The galaxies farther out are moving in the same direction. The peculiar velocities of galaxies across a region spanning hundreds of millions of light-years all share a common component, a shared drift toward a single region of sky. That is not random. That is gravity, operating on a scale the textbooks of the mid-20th century had not accounted for. The idea that this motion even exists required careful measurement to establish. If you simply look at a galaxy through a telescope and measure how fast it is receding, you get a combination of two things: the expansion of space and the peculiar velocity. Separating the two requires an independent distance measurement, something that does not depend on how fast the galaxy is moving. Without that, you cannot tell whether a galaxy is farther away because the universe is bigger or because it happens to be moving away from you. When astronomers developed reliable ways to measure distances independently, they found residuals in the velocity data. Galaxies were not exactly where the expansion model said they should be. The leftover motion, after subtracting the expansion, was not random noise. It was a systematic signal. Something coherent was happening across an enormous volume of space. Here is the picture as it stood by the early 1980s. Astronomers had accumulated enough data to see that the Milky Way, the local group, the surrounding clusters, and galaxies stretching out for roughly 300 million light-years in a particular direction were all sharing a common extra velocity. Not all the same speed. Objects at different distances and angles showed different magnitudes, but all pointed more or less toward the same region of sky. The pattern was consistent with a gravitational source, something massive enough to exert a measurable pull across a volume of space that large must have been extraordinary. The Milky Way alone contains roughly 1 trillion solar masses. Whatever was doing the pulling had to dwarf that figure by an enormous margin to exert this kind of influence across such distances. No known structure at that time accounted for it. The Virgo cluster, the nearest large galaxy cluster to the Milky Way, was a known gravitational influence. But the Virgo cluster was not nearly large enough to explain a bulk flow of this magnitude. The numbers pointed somewhere else, somewhere farther, somewhere in a direction that would turn out to be one of the most frustrating regions of the sky for an astronomer to study. Something was out there, something massive and unseen, and it was pulling on everything within hundreds of millions of light years with a grip that nobody had predicted. In 1986, a team of 7 astronomers did something that sounds straightforward on paper and turned out to change the way we understand the architecture of the universe. Their names were David Burstein, Roger Davies, Alan Dressler, Sandra Faber, Donald Lynden Bell, Roberto Turlevich, and Gary Wegner. They would come to be called the 7 Samurai, not by themselves, but by the astronomical community that followed their work with increasing disbelief. What they set out to do, at least on the surface, was measure distances, not to a handful of galaxies, not to a few dozen, but to 400 of them. Elliptical galaxies specifically, scattered across an enormous swath of the sky. The ambition of this alone was enough to raise eyebrows. In 1986, measuring distances to 400 galaxies was not a weekend project. It was years of observing time, years of data reduction, years of arguing over methodology in rooms full of people who disagreed about almost everything except the importance of getting this right. The method they used is called the dn sigma relation. The name is less important than what it does. It exploits a physical property of elliptical galaxies that turns out to be surprisingly reliable. The size of an elliptical galaxy, measured in a specific way, correlates tightly with the speed at which stars inside it are moving. Fast-moving stars in a large, bright galaxy. Slower-moving stars in a smaller, dimmer one. Because this relationship holds across elliptical galaxies generally, if you measure how fast the stars in a galaxy are moving, you can calculate how physically large the galaxy must be. And if you know how large it actually is, and you compare that to how large it appears in the sky, you can work out how far away it is. Distance, without needing to know anything about how the galaxy is moving through space. This is the key. The dn sigma relation gives you an independent distance estimate. It does not care about redshift. It does not assume anything about the galaxy's motion. It just uses the physics of the stars inside it to tell you how far away you are. This matters enormously because of what you do next. Once you have an independent distance, you measure the galaxy's redshift separately. Redshift tells you how fast the galaxy appears to be moving away from you, combining the expansion of the universe with any additional motion the galaxy has on top of that. Subtract the expansion, and what is left over is the peculiar velocity. The part of the motion that cannot be explained by the universe simply growing. That remainder is what the seven samurai were after, not the expansion, the deviation from it. 400 galaxies, each one a data point, each one carrying inside it a small signal about whether it was moving faster or slower, toward or away from the observer, than pure expansion would predict. The work took years. Observing time on major telescopes had to be scheduled and fought for. Data had to be collected at multiple facilities across multiple observing seasons. Measurements had to be cross-checked against each other. The dn sigma relation, while reliable, introduced its own uncertainties, and those uncertainties had to be understood, quantified, and accounted for before any conclusions could be trusted. There was also the question of Malmquist bias, a statistical artifact that creeps into galaxy surveys when brighter objects are preferentially included in a sample, skewing the results in ways that can look like real physical signals. The seven samurai knew about this. Correcting for it was not straightforward. When they finally compiled the results and plotted the peculiar velocities of their 400 galaxies across the sky, something stopped them. The data was not random. It was not the scattered noise you would expect if the galaxies were simply jostling around in isolated groups, each doing its own thing. The peculiar velocities had a pattern, a coherent one. Across an enormous volume of space, hundreds of millions of light years across, galaxies were moving in the same direction. Not every single one, and not in a perfectly uniform way, but the signal was there, and it was unmistakable. A bulk flow, an entire region of the universe drifting in concert toward a specific point on the sky. The velocities they measured ranged from roughly positive 700 kilometers per second to negative 700 kilometers per second, depending on where in the sky you looked relative to that convergence point. Galaxies on the near side of the structure, between us and whatever was pulling everything, were moving away from us faster than expansion alone could account for. Galaxies on the far side were moving toward us, slowed by the pull of the same source. The pattern was the signature of a gravitational well. Something massive, sitting at a specific location, pulling everything in its neighborhood toward it. The mathematical signature of what you would expect if there were a concentration of mass enormous enough to distort the velocity field of galaxies across hundreds of millions of light years. They gave it a name, the Great Attractor. The name was partly a description and partly an admission of ignorance. They could not see it. They could not point to a single galaxy or cluster and say, "There, that is the thing doing this." What they had was a velocity field, a pattern in how galaxies were moving, pointing like a compass needle toward a region of sky. The name reflected what the data required, something attracting, on a great scale, with enough mass to pull the known universe around it like a slow tide. Something was out there in the direction of the constellations Norma and Triangulum Australe, behind the obscuring disk of our own galaxy, and it was massive enough to set hundreds of thousands of galaxies in motion toward it simultaneously. The paper the Seven Samurai published landed in the astronomical community like a stone dropped into still water. Some colleagues were skeptical. The systematic uncertainties in the dn sigma method were real, and a result this dramatic invited scrutiny. But the data held up under repeated examination, and the debate shifted from whether the bulk flow was real to what on earth could be causing it. They had found the gravitational engine behind the bulk flow, given it a name, and immediately run into the problem that would define Great Attractor research for the next decade. They could not see it. Every galaxy in the universe is doing two things at once. The first thing is straightforward. The universe is expanding, and every galaxy is being carried outward with it. This is not motion through space in any ordinary sense. It is space itself stretching, the way dots painted on a balloon move apart from each other when you blow it up. The farther a galaxy is from us, the faster it appears to recede. This relationship was mapped by Edwin Hubble in the late 1920s, and it holds across the entire observable universe. It is called the Hubble flow, and for a long time, astronomers treated it as the dominant fact about how galaxies move. The second thing is the one that caused decades of confusion. On top of this expansion, galaxies have their own individual motions, small deviations from the smooth Hubble flow caused by the gravitational pull of nearby mass concentrations. These deviations are called peculiar velocities. The word peculiar here is used in its older scientific sense, meaning particular or specific, not strange. But given what these velocities revealed, strange would not be wrong either. Measuring a peculiar velocity requires two separate measurements. First, you need to know how fast a galaxy appears to be moving away from you, which comes from its redshift, the stretching of light caused by recession. That number is easy to get. Second, you need an independent measurement of how far away the galaxy actually is, so you can calculate how fast it should be receding based on Hubble expansion alone. The difference between what you measure and what expansion predicts is the peculiar velocity. Get the distance wrong, and the peculiar velocity you calculate is fiction. This is why the Seven Samurai's careful work with elliptical galaxy distances mattered. They were trying to get the second number right. When they did, the pattern was unmistakable. Galaxies across a vast region of space were not moving in random directions. They were streaming. Depending on where in the sky you looked, the peculiar velocity of a galaxy might be plus 700 kilometers per second, meaning it was moving toward a common point faster than expansion predicted, or minus 700 kilometers per second, meaning it was lagging behind, dragged back against the flow. The range ran from roughly negative to positive 700 kilometers per second, and the direction of that range was not random. It was organized. It pointed somewhere. Now, how do you know this pattern is real and not just noise in your measurements? This is where the cosmic microwave background becomes indispensable. The CMB is the oldest light in the universe. About 380,000 years after the Big Bang, the universe cooled enough for electrons and protons to combine into neutral hydrogen, and suddenly the universe became transparent. The light released at that moment has been traveling ever since, stretched by expansion into microwave wavelengths. It fills all of space equally. From any truly stationary point in the universe, The CMB should look almost perfectly uniform in every direction, the same temperature of about 2.7 Kelvin, no matter where you aim your detector. But if you are moving, the CMB does not look uniform. It looks very slightly warmer in the direction you are traveling toward, and very slightly cooler in the direction you are traveling away from. This is the Doppler effect applied to the afterglow of the Big Bang itself. The effect is tiny. We are talking about temperature differences measured in thousandths of a degree, but it is real, and it is measurable, and it tells you something precise. It tells you your velocity relative to the rest frame of the early universe. When astronomers measured the CMB with enough precision to detect this asymmetry, the result was striking. The Milky Way has a net motion of roughly 600 kilometers per second in a specific direction relative to the CMB rest frame. One side of our sky tests fractionally warmer. The other side tests fractionally cooler. The CMB is not telling us about expansion. Expansion is uniform and cancels out. It is telling us about something else. It is telling us that our entire galaxy has an additional velocity, a peculiar velocity, pushing it toward a particular region of space. This gave astronomers something more powerful than a map of galaxy velocities. It gave them a reference. The CMB is the universe's own coordinate system, a fixed backdrop against which any motion can be measured cleanly. And against that backdrop, the Milky Way is moving fast, and it is not moving alone. The galaxy clusters the Seven Samurai had surveyed were also moving, all in roughly the same direction, their peculiar velocities adding up to a coherent bulk flow across hundreds of millions of light years. The signal was not in one galaxy or two galaxies. It was in a region of space so large that the only explanation was something massive sitting at the far end of it, pulling on everything within range. Something was generating that pull. The numbers pointed to a mass concentration enormous enough to drag galaxies across hundreds of millions of light years, accelerating everything in its basin toward the same gravitational sink. The CMB confirmed that the motion was real. The galaxy surveys confirmed that it extended across a staggering volume of space. The fingerprint was there, clear and organized, repeating at every scale astronomers could measure. The direction this motion pointed, the source of the gravity driving hundreds of millions of light years of galaxies toward the same spot, was sitting directly behind the worst possible obstruction in the observable sky. The most inconveniently placed obstacle in observational astronomy is not a distant nebula or a far-off galaxy cluster. It is our own galaxy. When the Seven Samurai published their results in 1986 and pointed at a region of sky and said, "Something enormous is there," the first instinct of the astronomical community was to look. Point a telescope in that direction. Find out what is doing the pulling. This is normally how science works. You identify a gravitational effect, you trace it back to its source, and you look at the source directly. What happened instead was that astronomers pointed their telescopes toward the Great Attractor and ran directly into a wall of their own galaxy. The Milky Way is not a transparent structure. From above, it would look like a flat disk of stars and gas spiraling outward from a dense central bulge. From inside, which is where we are, it looks like a bright band of light cutting across the night sky. That band is beautiful. It is also, for observational astronomy, something close to catastrophic when the object you need to study happens to sit behind it. The disk of the Milky Way is packed with interstellar dust. These are not the dust bunnies under a sofa. These are vast clouds of microscopic solid particles, silicates and carbon compounds, distributed throughout the galactic plane in quantities thick enough to block visible light almost completely. When light from a distant galaxy tries to pass through this material, it does not make it through. The photons scatter, they absorb, they disappear into the cloud. By the time a ground-based optical telescope looks toward the galactic plane, it is staring at a ceiling with no way to see past it. Astronomers call this region the Zone of Avoidance. The name is accurate. For most of the history of extragalactic astronomy, surveys simply skipped this part of the sky. There was no point including it. Anything behind the disk was invisible. Galaxy catalogues developed holes in the shape of the Milky Way's plane, blank regions where the data simply stopped. This was accepted as a limitation and mostly ignored, because the galaxies visible in the unobscured sky provided enough science to occupy generations of researchers. Then the Great Attractor was discovered, and the Zone of Avoidance stopped being a minor inconvenience and became the central problem in an entire field. Think of it this way. Imagine you are trying to find the source of a sound that is clearly coming from somewhere in a fog bank. You can hear it on your instruments. You can measure how the sound bends the motion of everything around it. You can map, with precision, the direction the sound is coming from. But the fog stretches across exactly the region you need to look into, and you cannot see anything in it at all. You can tell from the pattern of deflections around the fog that the source is somewhere in the middle of it. You just cannot get your eyes on it. That is what astronomers were dealing with after 1986. The gravitational fingerprint of the Great Attractor was unmistakable. Its direction was known. Its approximate distance was estimated. But the region of sky it occupied was sitting directly inside the Zone of Avoidance, hidden behind roughly 10 to 20 degrees of latitude on either side of the galactic plane, a band covering something close to 20% of the entire sky. In the specific direction of the Great Attractor, the obscuration was severe enough that entire galaxy clusters could be sitting in plain sight and never appear in any optical catalogue. This was not a minor gap. Researchers throughout the late 1980s and into the 1990s worked to map the surrounding territory. They measured galaxy velocities in the regions flanking the Zone of Avoidance. They traced the flow lines. They built increasingly detailed models of what the gravitational source must look like, based entirely on the distortions it was producing in the galaxies around it. The models pointed consistently to the same location. The mass concentration had to be there, in the zone, in the gap, in the one patch of sky their instruments could not reach. What made this particularly maddening is the asymmetry of the situation. Astronomers were not trying to study a small, faint, marginal object. They were trying to study what appeared to be the dominant gravitational structure within hundreds of millions of light years, the engine driving the bulk motion of our entire cosmic neighborhood. By any measure, this was the most important thing in the local universe to understand. And it was hiding behind the one obstacle nobody had thought to prepare for, because nobody had anticipated that the target would end up precisely there. Some researchers attempted optical workarounds. They searched for windows in the dust, gaps where the obscuration was thinner, places where careful observation might allow a partial view through the zone. A few objects were found this way. They helped build a partial picture, but the core of the Great Attractor region remained stubbornly out of reach for conventional telescopes. The problem was not going to be solved by looking harder in visible light. The only path through was to stop using instruments designed for visible light and start looking at the universe in a completely different way. X-rays cannot be stopped by the same material that makes the zone of avoidance impenetrable to visible light. The dust and gas clogging the Milky Way's disk are enormously effective at absorbing and scattering optical photons, the kind of light human eyes are built to detect, the kind that ground-based telescopes had relied on for centuries. But X-rays are a different class of radiation entirely. They carry far more energy. They punch through interstellar dust the way hard radiation punches through thin cloth. When astronomers began putting X-ray detectors in orbit, above Earth's atmosphere, where X-rays can actually be detected, they were handed something that optical astronomers in the 1980s could only dream about: a way to look through the obstruction that had been hiding the Great Attractor for decades. This was not an overnight development. X-ray satellites had to improve considerably before they could map faint, distant galaxy clusters in a region as crowded and obscured as the Great Attractor direction. Early instruments lacked the resolution and sensitivity needed to pick individual clusters out of the noise. But by the late 1990s, the technology had advanced enough to make systematic surveys worthwhile. A dedicated program called the Clusters in the Zone of Avoidance Project, CIZA, set out to map exactly what was hiding behind the galaxy's disk. The goal was specific: find galaxy clusters, catalogue their positions and rough masses, build a picture of the large-scale structure in the one region of sky that optical surveys had been forced to leave blank. What CIZA and similar X-ray surveys revealed was a region of space far more populated than the blank patches on optical maps had suggested. Clusters that had no optical counterpart in any catalogue. Structures that had been invisible for the simple reason that nobody had been able to look at them began appearing in the X-ray data. The zone of avoidance was not empty. It had simply been waiting for the right instrument. Then came the revision that stopped astronomers cold. In 2005, researchers working with data from the CIZA survey published a result that forced a fundamental rethink. The mass of the Great Attractor, they reported, was roughly 1/10 of what the original 1986 estimates had placed it at. Not a slight correction, not a refinement at the margins, a reduction by a factor of 10. If the original picture had been of a gravitational engine with the mass of roughly 10 quadrillion suns, the new picture placed it closer to 1 quadrillion, still staggering by any human measure, but dramatically smaller than what the peculiar velocity maps had seemed to imply. This raised an obvious and uncomfortable question. If the actual mass was only 1/10 of the estimate, why had the peculiar velocities pointed so insistently toward this region? Part of the answer was a statistical artifact called Malmquist bias. When astronomers survey the sky for galaxies, they inevitably find more of the bright ones. That is not a flaw in technique. It is a simple consequence of how detection works. Faint objects at great distances fall below the threshold of any instrument. The survey only catches the luminous fraction. The problem is that this skews the sample in a systematic way. Galaxies that appear in the catalogue are not a random cross-section of the real population. They are drawn from the brighter end of the distribution. When you calculate distances and peculiar velocities using this biased sample, you overestimate the mass concentrations responsible for the observed motions. The original Great Attractor mass figures had been built partly on a foundation of this effect. When the X-ray surveys counted mass more directly, through the temperature and distribution of hot gas in galaxy clusters rather than through galaxy brightness, the number came down sharply. This did not mean the Great Attractor was an illusion. The bulk flow was real. The peculiar velocities were real. Something out there was pulling. But the revised picture was more complex than a single monolithic mass concentration. The pulling was being done by a combination of structures spread across a larger region of space. With no single dominant object of the scale the early models had assumed. The X-ray surveys were not deflating the mystery so much as redistributing it. What they did find, in the heart of the obscured region, was a specific object massive enough to serve as a gravitational anchor for the whole area. The Norma Cluster, catalogued as ACO 3627, showed up clearly in X-ray observations as the dominant mass concentration in the Great Attractor direction, sitting approximately 220 million light-years away, behind the dust that had hidden it for decades. It was the most massive galaxy cluster in the local universe within that region of sky. Optical follow-up, using near-infrared wavelengths that could partially penetrate the dust, confirmed what the X-ray data had indicated. There was a real, enormous structure there. After years of working with inferred gravitational effects and blank patches on maps, astronomers finally had something concrete to aim their instruments at. This was a pivotal moment in Great Attractor research. The problem had gone from an invisible gravitational disturbance with no known source to a known object with measurable properties. The Norma Cluster was real, locatable, and enormous. It was the most tangible thing in a region that had spent the better part of 2 decades resisting every attempt at direct observation. And what the X-ray surveys found at the center of the Great Attractor region was not the smooth, featureless mass concentration the original models had predicted. It was something with structure, texture, its own strange drama. At the heart of the Great Attractor region sits the Norma Cluster, and the first time you look at the numbers describing it, your instinct is to check whether they are correct. The cluster carries the formal designation ACO 3627. It sits roughly 220 million light-years away, behind the Zone of Avoidance, in the direction of the constellation Norma. For decades, the dust and gas of our own galaxy's disk hid it almost completely. When X-ray observations finally cut through, what they revealed was the most massive galaxy cluster in the local universe. The mass of the Norma Cluster is approximately 1,000 trillion solar masses. That number needs unpacking, because as written, it means almost nothing. Our Sun is not a small star. Nearly all of the solar system's mass, approximately 99%, belongs to our Sun. 1,000 trillion of those suns packed into a single gravitational structure. The entire Milky Way, every star in it, every gas cloud, every dark corridor between the spiral arms contains roughly 1 trillion solar masses. The Norma Cluster outweighs the Milky Way by a factor of 1,000. If you somehow collected 1,000 complete copies of our galaxy, every star and every planet in all of them, and compressed them into a single bound system, you would approach what is sitting at the center of the Great Attractor region. That is what the X-ray satellites found hiding behind the zone of obscuration. Pause to consider what follows carefully. The light crossing the Norma Cluster right now, the light from one galaxy hitting the outer edge of another as they slowly merge, left those galaxies 220 million years ago to reach us. At that time, the dominant animals on Earth were early dinosaurs. That is how far away something is, while still being, by the standards of the Great Attractor, essentially the local neighborhood. But the Norma Cluster is not the whole story. It is the dense core, the most massive single structure, the hub. Around it extends something larger. Astronomers call it the Norma Wall, and sometimes the Great Attractor Wall. It is a filamentary sheet of galaxies and clusters spreading out from the Norma Cluster in multiple directions, crossing the sky behind the Zone of Avoidance, extending across the constellations of Centaurus and Vela. Other clusters are embedded along this wall. Pavo 2 lies along it. The Centaurus Crux cluster is part of it. The cluster designated CIZAJ 132.4.7-5736 extends the structure further still. The Norma Wall is not a collection of independent objects that happen to be near each other. It is a coherent, large-scale structure, a gravitational family whose members share a common origin in the density fluctuations of the early universe. Taken together, the estimated diameter of this wall spans roughly 300 million light-years. The Milky Way, for comparison, is about 100,000 light-years across. The Norma Wall is 3,000 times wider than our entire galaxy. None of this is the most important thing about the Norma Cluster. The most important thing is what you cannot see. The 1,000 trillion solar masses of visible material, the colliding ellipticals, the radio-bright collision zones, the gas halos detectable in X-rays, all of that represents the luminous fraction, the part that telescopes can actually register. Underneath it, threading through it, extending far beyond its visible edges in every direction, is a dark matter halo whose mass dwarfs what any instrument has directly observed. The visible cluster is something like the foam on top of a wave. The wave itself, the true gravitational engine, is the dark matter concentration. We cannot see it. We infer its presence from the way visible matter moves, from the depth of the gravitational well, from the way light bends around the region. But without it, the numbers would not work. A cluster of 1,000 trillion solar masses in visible material would require a dark matter envelope several times larger to produce the gravitational effects actually measured. The Norma Cluster was the anchor, the most concrete object in a region that had spent decades resisting observation, but it was only the visible face of something whose true mass was mostly invisible. The numbers used to describe the Great Attractor stop making intuitive sense almost immediately. That is the universe's way of telling you that your intuitions were built for the wrong scale. The Norma Cluster alone holds roughly 1,000 trillion solar masses. That figure already strains comprehension. But the Norma Cluster is only the visible core of a much larger region. The region as a whole carries a mass estimated at around 10,000 trillion solar masses, written out. That is a 10 followed by 16 zeros. There is no everyday comparison that survives contact with a number like that. You have to build your way up to it slowly, the way you might let your eyes adjust to darkness. Start with something familiar. Our Sun is a fairly ordinary star. It is not especially massive, not especially large. The Milky Way contains roughly 1 trillion stars in that general range. When you add up all the stars, all the gas, all the dust, all the dark matter holding the galaxy together, you get a total mass of approximately 1 trillion solar masses. 1 trillion. That is the full weight of everything in the galaxy you live inside, every star you have ever seen in the night sky, every nebula ever photographed, every black hole astronomers have ever measured. The Milky Way is not small, and the Great Attractor region outweighs it by a factor of roughly 10,000. 10,000 Milky Ways stacked together would match the gravitational weight of the structure pulling us across the cosmos right now. The diameter is just as difficult to hold in your mind. The Milky Way stretches approximately 100,000 light-years from one edge to the other. That distance is already so large that light, traveling at 300,000 kilometers per second, needs a full 100,000 years to cross it. The Great Attractor region spans an estimated 300 million light-years. To cross the Great Attractor from one side to the other at the speed of light would take 3,000 times longer than the entire current age of the universe. Put differently, the Great Attractor is roughly 3,000 Milky Ways wide. If you place the Milky Way inside the Great Attractor region and tried to find it, it would be invisible. Not because it is faint, but because it would occupy a volume so small relative to the whole that it would be statistically irrelevant. Here is something worth sitting with. Light leaving one edge of the Great Attractor region today, headed toward the other edge, will not arrive until long after the Earth has been swallowed by an aging sun. The structure is so wide that no signal, no message, no observation made from one side could reach the other within a time frame that means anything to human civilization. The Great Attractor does not fit inside human time. It barely fits inside cosmic time. Now comes the stranger part. Of all that mass, 10,000 trillion solar masses, roughly 85% of it produces no light whatsoever. It does not emit. It does not absorb. It does not reflect. Every telescope ever built, from Galileo's first tube to the mirrors of the James Webb Space Telescope, is completely blind to it. This is dark matter. In the Great Attractor region, it is not a minor component or a marginal correction to the visible mass. It is the overwhelming majority of what is there. The galaxies, the clusters, the colliding ellipticals of the Norma Cluster, radiating their radio waves across millions of light-years. All of that visible material accounts for only about 15% of what is doing the pulling. What we can see is an afterthought. The real structure is invisible. Think of it this way. Imagine an enormous sphere of completely transparent material, something with no color, no shine, no surface you could ever detect with your eyes. Now scatter a thin layer of glowing dust across the outside of that sphere. What you would see, looking from a distance, is the dust. That is what astronomers see when they look at the Great Attractor region. The galaxies are the dust. The sphere they are draped across is the dark matter halo underneath. The halo is immeasurably larger and heavier than everything visible combined. This means the maps astronomers made of the Great Attractor region in visible light were telling a deeply incomplete story. The X-ray surveys that identified the Norma Cluster, the optical catalogues that traced the Norma Wall across multiple constellations, they were mapping the dust on the surface. The structure doing the actual gravitational work, the thing exerting that 10,000 Milky Way pull across hundreds of millions of light-years, was sitting underneath the visible galaxies, silent and undetectable by any direct means. Astronomers inferred its presence from its effects, the way you might infer the existence of a strong wind by watching everything in the room move in the same direction without being able to feel the air itself. What made this realization so significant was not just its strangeness. It was what it implied about the architecture of our local universe. A structure this massive, this wide, hiding most of its substance in invisible matter, drawing in galaxies from hundreds of millions of light years in every direction. That is not an accident of cosmic geography. Gravity does not accidentally build something that large out of random noise. What the Great Attractor represented, once the scale came into focus, was a node, a place where the large-scale structure of the universe converges, where filaments of matter and dark matter meet and pile up, where the gravitational logic of the cosmos makes a kind of focal point. This was not a random anomaly in an empty corner of the universe. It was the center of something organized on a scale that required a completely new map. In September of 2014, a team of astronomers published a paper that quietly redrew the map of the universe as far as it concerns us. The lead author was Brent Tully, an astronomer at the University of Hawaii who had spent decades studying the large-scale distribution of galaxies. His collaborators included researchers from France, Israel, and the United States. What they published was not a new observation of a distant object. It was something more fundamental than that. They had found a new way to ask a very old question. Where do we actually live? And how large is it? The question sounds simple. It is not. For most of the 20th century, the concept of a supercluster was loosely defined. Astronomers used the word to describe regions of space where galaxies seemed to cluster more densely than average, but the boundaries were subjective. There was no clean method to say where one supercluster ended and another began. You could draw the lines almost anywhere and find someone who would argue with you. Tully's team changed this by switching the question entirely. Instead of asking where the galaxies are, they asked where the galaxies are going. The technique they used was built around galaxy flow patterns. Every galaxy has a peculiar velocity, a motion above and beyond the simple expansion of the universe. That motion is caused by gravity. Galaxies are pulled toward mass concentrations, which means that if you map which direction thousands of galaxies are moving, you can reverse engineer the gravitational landscape beneath them. Tully's team compiled data on the peculiar velocities of roughly 8,000 galaxies across a vast region of space and used that data to draw the gravitational watershed lines. A watershed, in geography, is a boundary that separates water flowing into one basin from water flowing into another. The team applied the same concept to galaxies. Any galaxy whose flow pointed inward toward the same gravitational minimum was part of the same supercluster. Any galaxy whose flow pointed away, draining toward a different basin, was not. The result was a supercluster defined not by proximity or density, but by gravitational allegiance. What they found was enormous. The structure they mapped spans roughly 500 million light-years. That number is worth holding for a moment. The Milky Way is about 100,000 light-years across. The distance to the nearest large galaxy, Andromeda, is about 2.5 million light-years. The distance to the Virgo cluster, the nearest major cluster, is about 65 million light-years. Laniakea contains all of this and extends roughly 8 times farther still in every direction from its center. It holds more than 100,000 individual galaxies. The total mass is estimated at around 100 million billion times the mass of our Sun. The Milky Way, with its few hundred billion stars, is one small tributary in this structure. They named it Laniakea. The word comes from Hawaiian. Lani means heaven. Akea means immense or spacious. Immense heaven. The name was not chosen arbitrarily. Tully had strong connections to Hawaii through his work at the university there, and the language has a tradition of naming astronomical features. The name fits. There is something appropriate about a structure this large being described with a word that gestures toward the sky rather than toward any earthly measure. The paper came with a visualization that got considerable attention when it was published. Researchers rendered the flow lines of thousands of galaxies as streams, each one a thin tendril curving through three-dimensional space. What the image showed was something that looked unmistakably like a drainage system. The streams flowed inward from every direction, curling and converging toward a single point. Some streams were short and nearly straight. Others traced long, arcing paths across hundreds of millions of light years before bending toward the center. All of them pointed toward the same place. That place was the Great Attractor. The Milky Way appears in that visualization as one small stream among thousands, located in the outer regions of the basin, already moving inward, already falling. Laniakea is not, however, gravitationally bound. This is a critical distinction. Being part of the same gravitational basin is not the same thing as being locked together permanently. The outer regions of Laniakea are far enough apart that the expansion of the universe will eventually overcome the gravitational pull, and the structure will slowly be pulled apart over billions of years. The inward flow we see today reflects the current balance between gravity and expansion. It is not a permanent state. What Tully's paper captured was a snapshot, a moment in the long history of this structure when inward flow still dominates across its full extent. The redefinition also clarified something that had been somewhat muddled in the older literature. When earlier researchers referred to the Virgo Supercluster, they were describing a region that Laniakea now contains as one of its subsidiary components. The Virgo Supercluster, which had been considered our home supercluster for decades, turned out to be one lobe of something considerably larger. Our address in the universe had gained another line. We live in the Milky Way, in the local group, in the Virgo Supercluster region, in Laniakea, all of it flowing toward the center, which raised a question that the new map made unavoidable. If everything in Laniakea is draining toward the Great Attractor, what is pulling the Great Attractor? The answer turned out to be something even larger. When researchers mapped the flow lines of Laniakea and traced them inward toward the Great Attractor, they had assumed they were approaching the end of the chain. The Great Attractor was the gravitational center, the low point in the basin, the destination toward which everything nearby was draining. That picture was clean. It was organized. It was also incomplete. Because when astronomers looked at which direction the Great Attractor itself was moving, the answer came back the same as before. It was falling. Not randomly, not drifting, but falling in a specific direction, towards something sitting roughly 650 million light-years away, in nearly the same region of sky. That something is called the Shapley Supercluster, and the numbers describing it make the Great Attractor look modest. The Shapley Supercluster contains more than 8,000 individual galaxies, not 8,000 stars. Galaxies, each one a gravitational system holding anywhere from tens of millions to hundreds of billions of stars inside it. The combined mass of the Shapley Supercluster exceeds 10 million billion times the mass of our Sun. Written out, that number is a 10 followed by 21 zeros. The Great Attractor, for all the weight attached to its name, is substantially less massive. Within a radius of roughly 1 billion light-years from the Milky Way, nothing rivals Shapley. It is the most massive concentration of galaxies known to exist in our corner of the universe, and it has been pulling on everything around it for billions of years without anyone on Earth knowing it was there. The discovery changed how astronomers interpreted the Milky Way's peculiar velocity. The original picture, the one the Seven Samurai had built in 1986, attributed our galaxy's motion almost entirely to the Great Attractor. That was the dominant gravitational source. That was the explanation. But as surveys improved and researchers were able to look farther out and account for more of the mass distribution in the local universe, something shifted in the numbers. Our peculiar velocity, it turned out, was not coming from a single source. About 44% of it could be attributed to the Great Attractor and the Laniakea structure around it. The remaining 56% was coming from farther away. It was coming from Shapley. More than half of the gravitational pull moving our galaxy at 600 kilometers per second through space has nothing to do with the object that was identified as the cause. It is coming from something even larger, sitting even farther away, in a direction we have been looking past for decades. This realization forced a significant revision to the story. The Seven Samurai had not, in fact, mapped the influence of a single gravitational engine. They had mapped the combined effect of a hierarchy, two enormous structures pulling on the same region of space from different distances, their influences blending into a single velocity signal that pointed somewhere between them. The Great Attractor is real. Its gravitational effect is real. But it was never the full explanation. What makes this stranger is the chain it implies. Our galaxy is falling toward the Great Attractor. The Great Attractor is falling toward Shapley. Each object in this sequence is itself a component of something larger, caught in the gravity of something it cannot escape. There is something almost uncomfortable about the pattern when you trace it clearly. You might expect at some level of the hierarchy to find a resting point, some structure massive enough that nothing pulls it further along. Shapley, for a time, seemed like a candidate. It is the largest known concentration within 1 billion light-years. Nothing near it appears to have the mass needed to drag it out of position. But the universe is large enough that even this ceiling has a ceiling. Surveys of galaxy motions on scales larger than Shapley reveal bulk flows that extend beyond it, suggesting that even more distant mass concentrations are influencing the motion of the entire local region of the universe. The names for these structures, the Sloan Great Wall, the Hercules Corona Borealis Great Wall, begin to accumulate. Each one represents an overdensity, a concentration of galaxies and dark matter, pulling on everything around it at a distance where individual galaxies are too faint to see without the largest telescopes ever built. Whether there is a true end to this chain, some outermost gravitational source beyond which nothing pulls, is a question that observational cosmology cannot yet answer cleanly. What astronomers can say is that the local picture, the one centered on the Great Attractor, on Laniakea, on the bulk flow the seven samurai measured, is embedded in a larger gravitational landscape that does not stop at the edges of what any single survey has mapped. Shapley is the dominant known influence beyond the Great Attractor, and its contribution to our peculiar velocity is larger than the Great Attractor zone. That fact alone was enough to reshape how cosmologists think about large-scale structure in the nearby universe. The motion of our galaxy is not the signature of one object. It is the fingerprint of a nested system of gravitational pulls, each embedded in the next, reaching outward to distances where the edge of the observable universe starts to become relevant. The Shapley Supercluster sits about 650 million light-years away. Light left it when complex animal life on Earth was only beginning to take hold. That light is arriving now, carrying information about a structure whose gravity has been shaping the motion of our galaxy for longer than multicellular life has existed on this planet. The Great Attractor is falling toward it at a speed comparable to our own peculiar velocity. Our galaxy is falling toward the Great Attractor, and something beyond Shapley, something not yet fully mapped, may be pulling on all of it together. Every time astronomers thought they had found the ceiling of the hierarchy, another floor turned up above it. About 85% of the mass responsible for pulling the Milky Way toward the Great Attractor cannot be seen. Not because it is too far away, not because it is hidden behind the Zone of Avoidance. It cannot be seen because it does not interact with light at all. It does not emit light, absorb light, or reflect light. Every telescope ever built, in every wavelength from radio waves to gamma rays, returns nothing from this material. And yet it outweighs everything we have ever observed by a factor of roughly 5-to-1. This is dark matter, and without it, the Great Attractor would not exist, the Norma Cluster would not exist, and the Milky Way itself would long ago have torn itself apart. The first serious evidence appeared in the 1970s, when astronomers began measuring how fast stars move around the centers of their galaxies. The expectation was straightforward. Stars near the center of a galaxy, where most of the visible mass is concentrated, should orbit quickly. Stars far from the center, where visible mass thins out, should orbit more slowly. This is how the planets in our solar system behave. Mercury moves fast. Neptune moves slow. The math is clean. But when Vera Rubin and her colleagues measured actual stellar rotation curves in spiral galaxies, the curves came out flat. Stars at the far edges of galaxies were moving just as fast as stars near the center. They should have been flung outward into empty space by that speed, like water spraying off a spinning wheel. I were not. Something was holding them in. Something massive, distributed throughout the entire galaxy, including the outer regions, and completely invisible. The visible matter alone could not account for the gravity needed to keep those stars on their orbits. Rotation curves were only the beginning. Gravitational lensing provided a second line of evidence. When light from a distant object passes close to a massive structure, gravity bends the light, distorting the image in predictable ways. Astronomers can work backward from the distortion to calculate how much mass is doing the bending. When they did this with galaxy clusters, the mass required to produce the observed lensing was several times larger than the mass visible in stars and gas. Something invisible was bending the light. There was simply too much gravitational effect for the visible matter to explain. The structure of galaxy clusters made the case even harder to dismiss. Clusters like the Norma Cluster contain hot gas that moves between galaxies. The temperature and motion of that gas reflects the gravitational environment it is sitting in. When astronomers measured the temperature of the gas through X-ray observations, they found it was far too hot to be held in by the gravity of the visible galaxies alone. The cluster should have been blowing itself apart. The gas could only be that hot and still be retained if there was a much larger mass holding everything in place. Every method pointed to the same conclusion. Most of the mass in every galaxy, every cluster, and every supercluster is invisible. For the Great Attractor, this changes the picture significantly. When the Seven Samurai detected the bulk flow in 1986, they were measuring the gravitational pull of a structure whose total mass is somewhere around 10,000 trillion solar masses. The visible component of that, the galaxies you can count, the hot gas you can detect with X-ray satellites, the stars you can resolve, represents perhaps 15% of the total. The remaining 85% is a dark matter halo of staggering proportions, distributed through the region in a way no optical telescope can map. The Norma Cluster, the Norma Wall, the individual galaxies streaming toward the center, these are surface features. They are the thin, visible coating on an object whose true bulk is entirely hidden. Think of it this way. If you could somehow remove every galaxy in the Great Attractor region, every star, every cloud of gas and dust, the gravitational structure would still be there. The dark matter halo would remain, and it would still be pulling on the Milky Way at essentially the same rate. The galaxies are passengers, not the engine. What the Seven Samurai actually found in 1986 was mostly the gravitational signature of something that has never been seen and has not yet been detected in any laboratory on Earth, despite decades of experiments designed specifically to find it. This matters for understanding not just the Great Attractor, but the entire large-scale structure of the universe. The filaments, the voids, the walls of galaxies, the massive nodes where superclusters accumulate, none of this pattern emerged from ordinary matter alone. In the early universe, before the first stars formed, dark matter began clumping under its own gravity. Because it did not interact with light, it was not pushed around by radiation pressure the way ordinary matter was. It could collapse freely, pulling itself together into halos, while the visible matter was still too hot and too agitated to follow. By the time ordinary matter cooled enough to settle, dark matter had already constructed a scaffolding across the entire observable universe. Galaxies formed where the dark matter was densest. Filaments traced the dark matter filaments underneath them. Voids formed where dark matter was thin. The cosmic web we described earlier is, at its foundation, a dark matter web with visible matter painted onto it. The Great Attractor is one of the densest nodes of that web within several 100 million light-years of Earth. Its gravity is real. Its pull is measurable. But what you are being pulled by is mostly something for which we have no complete physical explanation. Something we have never held in a detector, and something that makes up the overwhelming majority of all the matter in the universe. Without the dark matter scaffolding, none of the visible structure we are describing would exist in the form it does, the Great Attractor included. There is a force working in the opposite direction from gravity on the largest scales, and given enough time, it wins. To understand what this means for the Great Attractor, You have to go back to 1998, when two independent teams of astronomers were doing something that sounded routine. They were measuring the brightness of distant supernovae, the catastrophic explosions of dying stars, to map how the expansion of the universe was changing over time. The standard assumption was straightforward. Gravity should be slowing the expansion down. The universe began with the Big Bang. Matter was flung outward, and gravity should be pulling that matter back, decelerating the whole thing like a ball thrown upward against the pull of Earth. The question was not whether the expansion was slowing. The question was, how fast? The answer came back wrong. Both teams, working independently with different telescopes and different data sets, found the same result. The distant supernovae were dimmer than they should have been. Not slightly dimmer, measurably, consistently dimmer. And in astronomy, dimmer means farther away. The supernovae were farther away than a decelerating universe had any right to put them. The expansion was not slowing down, it was speeding up. Something was pushing the universe apart at an accelerating rate, and nobody had predicted it. The teams spent months checking their data, looking for errors, looking for systematic mistakes in calibration. The result held. In 1998, the discovery was announced, and cosmology has not been the same since. The force responsible has a name, dark energy, and that name is essentially an admission that nobody knows what it is. What astronomers do know is this: dark energy makes up roughly 68% of the total energy content of the universe. Ordinary matter, the stars, the planets, the gas clouds, everything built from atoms, accounts for only about 5%. Dark matter, the invisible gravitational scaffolding described in the previous section, accounts for around 27%. The universe is, in terms of its energy budget, overwhelmingly made of something that has never been detected in a laboratory and has no agreed-upon physical explanation. Dark energy is the largest single component of the cosmos, and it is a mystery. What dark energy does is push. On small scales, gravity is stronger. A galaxy cluster holds together because the mass packed inside it generates enough gravitational attraction to overwhelm the push of dark energy at those distances. The Milky Way and Andromeda are gravitationally bound. The local group, the few dozen galaxies sitting nearest to us, are bound together. The Virgo cluster holds together. Gravity wins at those scales because the distances are short and the densities are high. But as you zoom out, the balance shifts. At scales of a few 100 million light-years or more, the expansion driven by dark energy begins to win over the gravitational pull tying structures together. Objects that are not tightly bound by gravity at those distances do not stay together. They drift apart. The expansion carries them away from each other faster than gravity can pull them back. This is where Laniakea becomes a problem. Laniakea, the supercluster containing the Milky Way, the Great Attractor, and more than 100,000 other galaxies spread across 500 million light-years, is not gravitationally bound. It looks like a coherent structure when you map the flow of galaxies toward the Great Attractor. It has a center, a basin, streams of galaxies draining inward like rivers toward a sea. But it is not held together the way a galaxy cluster is held together. The outer regions of Laniakea are already being pulled apart by the expansion of the universe. Given enough time, the structure will not survive as a unit. The rivers will reverse, the streams will scatter. For the Milky Way, this means something specific. Right now, we are moving toward the Great Attractor at roughly 600 kilometers per second. Every second of every day, our galaxy closes that distance by 600 kilometers. The pull is real, it is measurable, and it has been operating for billions of years. But the Great Attractor is not sitting still waiting for us to arrive. The space between us and that region is expanding. At the distance of the Great Attractor, somewhere between 150 and 250 million light-years, the recession due to cosmic expansion is already significant. Our approach speed and the expansion rate are working against each other, and dark energy is accelerating the expansion continuously. The gap is not shrinking as fast as the raw velocity would suggest. In some projections, it may not shrink at all, depending on how dark energy behaves on these timescales. Think of it as running toward a door that is sliding away from you down a corridor. You are running. You are getting closer in the sense that you are covering ground, but the corridor is stretching as you run, and the door is accelerating. You will not reach it. The universe has built a destination into the motion of our galaxy, and then quietly ensured that the destination remains unreachable. What this means in concrete terms is that the Milky Way will spend billions of years moving toward the Great Attractor and will never close the distance to zero. The gravitational pull will not vanish suddenly. It will weaken gradually as the distance grows, as the expansion carries the Great Attractor region farther and farther from us, as the geometry of the universe dilutes the grip of that enormous concentration of mass and dark matter. There is no arrival. There is only approach, and then eventually a slow fading of the pull itself. For a structure that has been shaping the motion of our galaxy since before the Earth existed, that is a strange kind of ending. Not a collision, not a merger, not a dramatic conclusion, just an increasing distance, a weakening signal, a gravitational whisper fading below the threshold of any influence. The countdown that governs our relationship to the Great Attractor is not the countdown to arrival. It is the countdown to the point where the pull becomes too weak to matter, and that clock runs on a different timescale than anything in human experience. Every structure in the universe is simultaneously a container for smaller things and a component of something larger. This is not a poetic observation. It is a description of how matter is actually organized, layer by layer, from the scale of a solar system out to the scale of superclusters spanning 500 million light-years. And once you start tracing the layers from the inside out, something unsettling becomes clear. Every level of the hierarchy is falling toward the next one up. There is no stationary floor. Start close. The Milky Way is not alone. It belongs to a collection of galaxies called the Local Group, roughly 50 members in total, most of them small dwarf galaxies clustered around two dominant structures, the Milky Way and the Andromeda Galaxy. The Local Group spans about 10 million light-years. By cosmic standards, that is a tight cluster. The Milky Way and Andromeda are already gravitationally bound to each other, already moving toward each other, already on a collision course that will play out in roughly 4.5 billion years. Everything in the Local Group is held together. Nothing escapes. This is the first container, but the Local Group is not sitting still relative to everything beyond it. The entire collection, Milky Way, Andromeda, all 50 members, is being drawn toward the Virgo cluster, a dense knot of more than 1,300 galaxies sitting about 65 million light-years away. The Virgo cluster is one of the most massive structures in the nearby universe, containing enough mass to pull our entire local group toward it with measurable force. The motion is slow relative to the distances involved. It will not result in a collision on any timescale worth discussing. But the pull is real, and it shows up in the data. The local group is not drifting randomly. It is drifting toward Virgo. Zoom out one level further, and the Virgo cluster reveals itself as the center of something bigger. The Virgo cluster, the local group, and the surrounding region of galaxies spread across roughly 110 million light-years form the Virgo Supercluster, also called the local supercluster. For decades, astronomers treated the Virgo Supercluster as the largest gravitational unit our galaxy belonged to. It was a reasonable conclusion. The structure was real, the mass was real, and Virgo sat at its center pulling everything inward. Then 2014 happened, and the map got redrawn. The 2014 paper that defined Laniakea didn't add new objects to the universe. It showed that the Virgo Supercluster was not a freestanding structure, but a tendril of something vastly larger. Laniakea spans roughly 500 million light-years, contains more than 100,000 galaxies, and has a total mass on the order of 100 million billion suns. The Virgo Supercluster is one piece of it. The local group is one piece of the Virgo Supercluster. The Milky Way is one piece of the local group. Each container fits inside the next one, and none of them are static. The flow lines that defined Laniakea's boundary showed something striking. Galaxies throughout this enormous volume are not moving randomly. They are draining inward, toward the center, the way water drains toward the lowest point in a basin. That lowest point is the Great Attractor. What does it mean to say that 100,000 galaxies are all drifting toward the same spot? Consider the distances involved. A galaxy on the far edge of Laniakea, 250 million light-years from the center, is still caught in that inward pull. Light from that galaxy takes 250 million years to reach us, which means the dinosaurs were not yet extinct when that light left its source. And the galaxy that produced it is, right now, moving toward the same gravitational basin we are moving toward. Everything within 500 million light-years is sharing a direction. Your address in the universe, properly written out, has more lines than most people expect. A planet, in a solar system, in a galaxy group, in a supercluster, inside a larger supercluster, all of it converging toward a gravitational center. And each line on that address is itself falling toward the line below it. The local group falls toward Virgo. Virgo falls with us toward the Great Attractor. The Great Attractor, along with all of Laniakea, falls toward the Shapley Supercluster, 650 million light-years away. Even the container falls towards something. The Shapley Supercluster is the most massive structure within roughly 1 billion light-years of Earth. It contains more than 8,000 galaxies and outweighs the Great Attractor by a considerable margin. It is pulling on Laniakea as a whole, bending the trajectory of every galaxy inside it, including ours. Calculations suggest that approximately 56% of the Milky Way's peculiar velocity, the motion above and beyond simple cosmic expansion, comes from Shapley's gravity. The Great Attractor accounts for most of the rest. We are not just falling toward one thing. We are falling toward a thing that is itself falling toward a larger thing, and that larger thing sits inside the cosmic web. surrounded by structures we have only recently begun to map. The cognitive experience of working through this hierarchy is difficult to describe cleanly. There is a moment when the nesting stops feeling like a neat organizational chart and starts feeling like something vertiginous. You realize that there is no privileged level, no natural stopping point where structure ends and emptiness begins. Every scale reveals another scale. Every container is contained, and the motion runs all the way up the chain. Nothing is exempt from the pull of the next level out. The Great Attractor sits at one of those convergence points, a node where the threads of the cosmic web pull tight, a gravitational crossroads drawing in everything for hundreds of millions of light years in every direction. If you could somehow step back to a distance from which the entire observable universe fits in your field of view, what you would see is not a smooth fog of galaxies uniformly distributed through space. What you would see is a web. Long luminous filaments stretching across hundreds of millions of light years, branching and intersecting at dense glowing nodes. Between those filaments, almost nothing. Enormous dark voids, some spanning hundreds of millions of light years, where matter was pulled away long ago and never returned. The structure looks organic. It looks almost biological. Scientists call it the cosmic web, and it is the largest known structure in the universe. This was not always expected. For much of the 20th century, the working assumption was that on large enough scales, matter would smooth out. Look far enough in any direction, and galaxies should be roughly evenly distributed. The universe should look more or less the same from any vantage point. This idea has a name, the cosmological principle, and it is still broadly true on the very largest scales. But on scales of hundreds of millions of light years, the universe is anything but smooth. It is lumpy, stringy, and punctuated by vast emptiness in a way that surprised many of the researchers who first mapped it. The first strong predictions of this web structure came not from telescopes, but from computers. In the 1980s, cosmologists running early numerical simulations of structure formation found that if you started with the right initial conditions and let gravity run for billions of years, matter did not spread evenly. It collapsed first into sheets, then into filaments, then into dense clumps at the points where filaments crossed. The simulations showed a web forming almost inevitably, driven by nothing more exotic than gravity, working on small initial differences in density. The pattern was striking enough that researchers took it seriously, even before observations could confirm it. What the simulations could not produce on their own was the right amount of structure. Ordinary matter alone, the protons, electrons, and neutrons that make up stars and gas and dust, did not collapse fast enough to build the web you actually see in the sky. Something else had to provide the scaffolding. That something was dark matter. Because dark matter does not interact with light, it began clustering under gravity earlier than ordinary matter did, before the universe had cooled enough for ordinary matter to follow. By the time ordinary matter could collapse, dark matter had already sketched out the structure. The filaments, the nodes, the voids, all of it was roughed in by dark matter first. Ordinary matter settled into those grooves afterward, the way water fills the channels carve, into rock. The observational confirmation came through large-scale galaxy surveys. In the 1990s and 2000s, projects like the 2DF Galaxy Redshift Survey and the Sloan Digital Sky Survey began mapping the three-dimensional positions of hundreds of thousands of galaxies across enormous volumes of space. The web was unmistakable. Filaments ran for hundreds of millions of light years. Voids sat between them, some nearly empty of any visible matter. At the intersections of multiple filaments, dense galaxy clusters sat like knots in a net. The maps looked almost exactly like what the computer simulations had predicted decades earlier. The match between theory and observation was one of the more striking confirmations in modern cosmology. Where did the web ultimately come from? Go back far enough and the answer lies in quantum mechanics. In the first fraction of a second after the Big Bang, the universe was not perfectly uniform. There were tiny random fluctuations in density, regions slightly denser than average and regions slightly emptier, produced by quantum processes at almost incomprehensibly small scales. These fluctuations were then stretched across the universe during a period of rapid expansion called inflation. What began as quantum noise became the seeds of cosmic structure. Over the next several billion years, gravity amplified those seeds. Slightly denser regions attracted more matter, grew denser still, and eventually collapsed into the filaments and nodes of the cosmic web. The voids grew emptier as matter drained away from them toward the filaments. The web you see in galaxy survey maps today is the cumulative result of gravity working on quantum fluctuations for roughly 13 billion years. The nodes of this web, the places where multiple filaments intersect, are where the largest gravitational concentrations in the universe sit. These are the superclusters, the places where the web pulls tight and matter has piled deepest. They are not random. They sit precisely where the geometry of the filaments forces them to be. When you have 3 or 4 massive filaments converging on the same region of space, the gravitational basin at that intersection will accumulate mass over billions of years until it becomes something on the scale of the Great Attractor. That is not a coincidence or an accident of initial conditions in some narrow sense. It is the inevitable output of a process that was set in motion in the first moments of the universe. The Great Attractor is one of the knots in that web, and its gravity is doing what gravity has always done and will always do, pulling the nearby universe toward the middle. Here is the strange part. Every second that passes, the Milky Way moves roughly 600 kilometers closer to the Great Attractor. Not the solar system, not just the sun, the entire galaxy, every star in it, every planet orbiting those stars, every person who has ever lived, covering 600 kilometers of ground every second, pointed at the same destination, without interruption, without slowing down. That has been true for billions of years. It will be true tomorrow. And despite all of it, we will never get there. The reason has to do with something that is happening at the same time, in the opposite direction. The universe is expanding. The space between the Milky Way and the Great Attractor is not fixed. It is growing continuously because the fabric of space itself is stretching. This is not the Great Attractor moving away from us the way a car pulls ahead on a highway. The road itself is getting longer. Every megaparsec of distance between us and the attractor region is adding roughly 70 kilometers per second of recession on top of whatever motion the galaxies have on their own. The Great Attractor is somewhere between 150 and 250 million light-years away. At that distance, the expansion of space is adding several thousand kilometers per second of separation between us. Our 600 kilometers per second approach has not come close to cancelling that out. We are running toward a destination that is receding faster than we can close the gap. Now add dark energy. Since 1998, astronomers have known that the expansion of the universe is not slowing down, it is accelerating. Whatever dark energy is, it is pushing the universe apart at an ever-increasing rate. That means the recession speed due to expansion is not a fixed number we are racing against. It is a growing number. Every billion years, the effective recession rate between us and structures at Great Attractor distances gets a little larger. Our approach speed does not increase to match it. The gap between what we can do and what the universe is doing to the space in front of us quietly widens. Think of it this way. Imagine walking toward a door at the end of a corridor. You are making steady progress. You can see the door getting closer. Then you notice that the corridor itself is stretching. The door is still there. You are still walking. But the floor beneath you is being pulled backward even as your legs move forward. At first, you are fast enough that the distance still shrinks. But the corridor keeps stretching faster, and your walking speed stays the same. Eventually, the door stops getting closer, and then, slowly, it starts to get farther away, even though you never stopped walking. That is roughly the situation we are in, on a scale that requires millions of light years instead of meters to describe. The numbers bear this out in a rough way. The Great Attractor sits approximately 250 million light-years out. Our peculiar velocity of 600 kilometers per second, if it were the only thing happening, would mean we are cutting the distance at a rate that sounds fast until you do the conversion. 600 kilometers per second is about 19 billion kilometers per year. 1 light-year is roughly 9.5 trillion kilometers. So we are closing in at about 2,000 light-years per year. At that rate, reaching something 250 million light-years away would take more than 100 billion years, well beyond the current age of the universe. And that calculation completely ignores the expansion working against us. In reality, the expansion is already adding separation faster than 600 kilometers per second, which means the true distance to the Great Attractor region is not shrinking at all. It is growing, just more slowly than it would be if we had no peculiar velocity. There is something worth sitting with here. This is not a matter of insufficient technology or inadequate propulsion. No spacecraft, no matter how fast, launched in any direction, could reach the Great Attractor before dark energy renders the journey impossible. The obstacle is not engineering, it is physics. The space between here and there is being manufactured faster than anything can cross it. The Great Attractor is, in a precise sense, not merely distant, it is unreachable. Its gravity reaches us. Its effects on our motion have been real for billions of years. But the place itself sits behind an expanding barrier that deepens every second. What makes this genuinely strange is the word attractor. In physics and mathematics, an attractor is something that nearby states converge toward over time. Systems fall into attractors. They do not hover indefinitely at some fixed remove from them. A pendulum dragged to the side swings back to center and stays. A ball placed on a curved surface rolls to the bottom. The Great Attractor is different. It exerts gravitational pull across hundreds of millions of light years, sets an entire supercluster's worth of galaxies moving toward its center, and then, because the universe is expanding underneath everything, never actually collects what it is pulling. The galaxies of Laniakea are draining toward this gravitational minimum the way water drains toward a plug hole, except the plug hole is slowly moving away from the water. The geometry does not allow convergence. It allows only an eternal, futile approach. Our galaxy has been making this approach since before the Sun formed. The Milky Way was already falling toward the Great Attractor when the first stars in it began to burn, and it has not stopped. The motion will continue through everything that happens to this galaxy, through the merger with Andromeda, through the long cooling of the universe, through changes that stretch across timescales with no useful human analogy. The approach is real. The gravity is real. The motion is real. The arrival is not. The Milky Way has been falling toward the Great Attractor for billions of years and will keep falling for billions more, and it will never arrive. Eventually, dark energy wins completely. Right now, the numbers still favor the Great Attractor. The pull is real. The 600 kilometers per second is real. The flow lines threading through Laniakea, the rivers of galaxies draining toward the center, all of it is real and measurable today. But the universe does not hold still. What dark energy does on long-time scales is not dramatic. It is patient. It does not shatter structures. It stretches the space between them, slowly, steadily, without interruption, until distances that were once meaningful become distances that are simply too large for gravity to cross. In a few billion years, something significant happens closer to home first. The Milky Way and the Andromeda Galaxy, currently approaching each other at about 110 kilometers per second, will collide. This is not a disaster in any human sense of the word. Galaxies are mostly empty space. The collision will play out over hundreds of millions of years, stars sliding past each other, gas clouds smashing together, new stars igniting from the compression. What emerges from the other side will be a single large elliptical galaxy. Astronomers sometimes call it Milky Way. It will be larger, rounder, and quieter than either of its predecessors, and it will still be moving toward the Great Attractor region. The merger does not change the bulk flow. The gravitational pull of the Norma Cluster and the dark matter concentration at the heart of Laniakea will still be there, still tugging. The combined remnant of our two galaxies will still be answering that pull, just as they do today. But the universe around Milky Way will look different by then. The nearest galaxy clusters beyond the local group will have receded significantly. The Virgo cluster, which today sits about 65 million light-years away and already contributes to the complex of gravitational forces shaping our motion, will be pulling away faster than any spacecraft could follow. The expansion of space does not care about gravity at those scales. Structures that are not tightly bound to each other will simply drift apart, the gap between them widening at an accelerating rate. There is nothing on any known physics that reverses this. Over tens of billions of years, the outer regions of Laniakea begin to dissolve. The supercluster is not gravitationally bound. This is the crucial detail. The Great Attractor pulls hard enough to shape the motions of galaxies across hundreds of millions of light-years today. But the structure it sits at the center of is not a closed system. It is a basin, and basins leak. The galaxies at the far edges of Laniakea, the ones whose infall velocity toward the Great Attractor is only slightly larger than the recession velocity from cosmic expansion, will at some point tip the other way, first slowly, then decisively, they will stop falling inward and start being carried outward. The flow lines that the 2014 Laniakea paper made so vivid. Those rivers of galaxies converging on a center will fray at the edges and then go silent. The Great Attractor region itself will not disappear quickly. The Norma Cluster and the dark matter mass at the heart of the structure will remain gravitationally bound within their local volume. Galaxies that are already tightly locked together will not be torn apart by dark energy on any timescale that astronomy currently considers. But the sphere of influence will contract. The radius out to which the Great Attractor can meaningfully compete with cosmic expansion will shrink over time. Everything beyond that shrunken boundary will simply be gone, carried over the horizon at faster than light recession speeds, unreachable and invisible. On timescales of trillions of years, the picture becomes stark. The universe will consist of isolated gravitational islands. Milky Way, along with the handful of smaller galaxies in the local group that are tightly bound to it, will persist. But the rest of the observable universe, everything beyond the local group, will have expanded beyond the cosmological horizon. No light from those structures will be able to reach us. No gravitational signal travels faster than light. If the source is beyond the horizon, its gravity effectively vanishes from our universe as a practical consideration. Any observers still present in that future will look out and see almost nothing. No galaxy clusters in the distance, no filaments, no sign that the cosmic web ever existed. The universe will look, to them, like an almost perfect void surrounding one small island of stars. The Great Attractor, the object whose gravitational fingerprint the Seven Samurai found in 1986. The object toward which our galaxy has been accelerating for billions of years, will by that point be entirely beyond any possible observation. Not because it collapsed, not because it exploded, simply because the space between it and Milky Way will have grown so vast that no signal of any kind could bridge it. The bulk flow will have ended. The peculiar velocity will have decayed to zero against the background of an expansion that has swallowed everything. All the structure we have spent this entire series of sections describing, the Norma Cluster, the Norma Wall, the Laniakea Basin, the convergence of flow lines toward a gravitational center, will be gone from any detectable universe, replaced by silence and an expanding void that contains no trace of what came before. Somewhere in that enormous stretch of future time, the last trace of the Great Attractor's gravitational influence will fall below any threshold that future observers could detect. The object that has been pulling our galaxy for billions of years will effectively cease to exist, not by collapsing or exploding, but simply by becoming too far away to matter. Step back from the distances and the dark matter and the mass figures that stopped meaning anything several sections ago. The Great Attractor is really a story about how incomplete our map of the universe kept turning out to be. For most of recorded human history, the night sky was the universe. Every point of light was something in our own galaxy, or so astronomers believed well into the 20th century. The debate about whether spiral nebulae were nearby gas clouds or distant galaxies in their own right was not settled until the 1920s, when Edwin Hubble measured the distance to Andromeda, and the answer came back staggering. Our galaxy was one among many. The universe was immensely larger than anyone had seriously proposed. That was the first time the map turned out to be wrong in a fundamental way. It would not be the last. By the middle of the 20th century, astronomers had organized galaxies into clusters and clusters into superclusters. The picture seemed reasonably complete. The Milky Way belonged to the local group. The local group belonged to the Virgo Supercluster. There was a structure, a hierarchy. It seemed like the kind of thing that could eventually be fully described. Then the Seven Samurai mapped the peculiar velocities of 400 galaxies and found that none of it was sitting still the way anyone expected. Everything was flowing. Something enormous was doing the pulling. It was sitting in a part of the sky nobody could see clearly. The map turned out to be wrong again. What the Great Attractor forced astronomers to confront was not just a missing object, it was a missing scale. The structures driving the bulk motion of our entire cosmic neighborhood were so large, so distant, and so thoroughly hidden that the tools and frameworks astronomers had built were not sufficient to find them. The zone of avoidance is not an exotic problem. It is our own galaxy blocking our view. The irony is almost mocking. The single most familiar structure in the night sky, the band of the Milky Way that humans have stared at since before writing was invented, turns out to be a curtain drawn across the most gravitationally significant region in the local universe. There is still a great deal that remains unresolved. The precise mass of the Great Attractor depends heavily on how you define its boundaries and how much of the signal in galaxy peculiar velocities you attribute to it versus to the Shapley Supercluster lying beyond it. The 2005 CIZA survey pushed the mass estimate down by a factor of 10 from early predictions. But how much of that revision was genuine and how much reflects the limits of X-ray surveys that still cannot fully penetrate the zone of avoidance is not entirely clear. The split between the Great Attractor's gravitational contribution and Shapley's, roughly 44% and 56% of our peculiar velocity respectively, is itself an estimate that has shifted as surveys improved and may shift again. And behind the zone of avoidance, there are still structures we have only partially mapped. Radio and X-ray observations have revealed pieces. The full three-dimensional picture remains incomplete. The nature of dark matter is its own open question sitting at the center of everything. Roughly 85% of the mass responsible for pulling the Milky Way toward the Great Attractor region is matter that has never been detected in any laboratory on Earth. Its existence is not seriously doubted by astronomers because the gravitational evidence for it is overwhelming. But what it actually is, what particle or particles, what properties beyond mass, remains unknown. The Great Attractor is, in a very direct sense, mostly made of something we cannot identify. When you ask what the Great Attractor is made of, the honest answer is, we are not sure. Step back even further, and the situation becomes something stranger than a scientific puzzle. Every person alive right now is on a planet orbiting a star inside a galaxy that is moving at 600 kilometers per second toward a gravitational structure it will never reach. Inside a supercluster that is itself not gravitationally bound and will eventually be pulled apart by the expansion of the universe. None of this motion is felt. None of it is visible without instruments of considerable sophistication. The ground underfoot gives no indication. The sky overhead gives no indication. You would have to be an astronomer with access to galaxy redshift surveys and a working knowledge of the cosmic microwave background just to know it was happening. There is something worth sitting with in that. The forces shaping the largest features of our cosmic address are entirely imperceptible at human scale. The Great Attractor pulls on our galaxy with a gravitational force that represents 10,000 times the mass of the Milky Way, across a distance of 150 to 250 million light-years. The result is a motion of 600 kilometers per second that no instrument aboard any spacecraft has ever measured directly. This was because it is a bulk motion. Every part of us moves together, so nothing inside the system registers the speed. It is only visible from outside, using other galaxies as reference points. That is a peculiar situation. Astronomy has been, for most of its history, the science of things that stay fixed while we watch them. The Great Attractor is something different. It is a destination. It is a direction. It is the center of a gravitational basin so large that it contains our galaxy, all of our nearest neighbors, roughly 100,000 other galaxies draining toward the same low point. And yet, it resists being pinned down. Its mass keeps being revised. Its structure is still being mapped. The dark matter that makes up most of it has no agreed-upon physical description. And the dark energy working against it guarantees that the journey toward it will never end in arrival. We cannot escape it. We cannot reach it. We cannot see most of it. We are not entirely sure what it is made of. And for now, that is the most honest summary of where things stand.